This is a course on basically introduction to primarily centrifugal pumps, but introduction to pumps in general. We'll be talking quite a bit about suction side conditions, overall total dynamic head, a lot of different things, cavitation, some troubleshooting. We're not going to go too far in depth being a basic course, but I want to give you a general understanding of, for instance, how to read a pump curve, how to be able to prevent some application problems such as not having enough NPSH or cavitation problems or minimum submergence. So we're going to talk about a lot of that stuff as we go forward. Okay, so in pump types, talking about types of pumps themselves, there's really two major classifications of pumps. There's positive displacement pumps, and the definition of that is that something physically moves into the space where the fluid was to be able to force that fluid movement down the line. So we have positive displacement and centrifugal pumps, and basically centrifugal pumps create movement by creating a difference in pressures, but it's done by an induction or influence rather than direct force. Now, a centrifugal pump can be stopped by just giving too much back pressure or too much resistance, such as closing a valve. It can stop all flow and generally survive, at least for a short period of time, whereas a positive displacement would have a severe problem with that. So as we move forward here, we're going to talk very briefly about positive displacement. Most of this course is about centrifugal pumps and applications there. So anyways, common types of positive displacement pumps, plunger or piston pumps. Generally, they're 2 or 3 plungers or 2 or 3 pistons with valving that operate on a progress, a alternating basis. Progressing cavity pumps, screw or gear pumps, diaphragm pumps. Those may be an electrically operated diaphragm or an air operated diaphragm. Rotary vane pumps, and peristaltic. And if we compare those types, and pump selection all the way through really is a series of trade-offs. And that's why there's so many different types of pumps, to be able to get to the best pump solution for a given application. But the the common traits, I should say, of positive displacement pumps are they're generally capable of producing very high pressures. They're generally very efficient. They must be pressure relieved with the exception of an air operated diaphragm pump, meaning that if you all of a sudden closed off the discharge of a pump, a positive displacement pump, you could get a pressure spike that would go to maybe several thousand PSI, maybe 50,000 PSI on a very short, quick basis. And something's going to give, piping's going to break, pump's going to break, something's going to break. So we put a pressure relief valve on most positive displacement. Again, the only exception to that is an air operated diaphragm pump. They have great suction priming characteristics almost always, meaning that they can prime themselves even from below pump level quite often. Typically, they are very close tolerance, again, with the exception of air operated diaphragm pumps. They cannot handle solids well at all, with the exception of diaphragm pumps can handle some. Most need lubrication from the fluid. They can't, some like gear pumps, for instance, wouldn't even operate on water because it's the lubricity of water is too low. And again, kind of an exception of diaphragm pumps. They can have a relatively short life compared to other types of pumps. Generally, they are special purpose positive displacements. Maybe handles things like toothpaste or paint, where it really needs to have some boost to the system to be able to move that fluid. Of course, pumping toothpaste is very thick, very high viscosity, and difficult to pump. Again, they must be pressure relieved. That's absolutely critical. Some pumps have the pressure relief valve in them. Positive displacement pumps have a pressure relief built into it. They are extremely vulnerable to cavitation because of those close tolerances and the pressures that they build. We'll talk a lot more about cavitation as we go forward. Again, this is just kind of a quick overview of positive displacement pumps. This is a kind of a quick overview of positive displacements and how they function under different constraints. In other words, do they handle solids, small solids, large solids? Is there a pulse to their flow? For instance, on a gear pump, there's generally a very low pulse to their flow, but on a piston pump, there's a very high pulse in that flow. In other words, flow moves and then it stops, and then it moves and it stops, rather than being a continuous flow. So this is a good comparison. We'll make all of this presentation available to you, as well as the video. We're recording this as we go forward here. So all of this will be available online, probably as a YouTube video, possibly on our LinkedIn page, and available for download. So you can take a look at some of these trade-offs that are made. Again, it's a series of trade-offs on pumps, whether positive displacements or centrifugals that happen on a normal course of base as you do the application selection, pump selection. Doing a centrifugal comparison between different types, there's the same type of chart here. Now we're going to get into centrifugals. Centrifugal, again, is something that induces flow rather than forces flow, if you will. And you'll see as we look down pulseless flow here, everything in a centrifugal pump is excellent. There is very little pulse to that flow. I mean, there may be a small minute amounts, but generally it's very smooth flow. It can handle, in certain cases, pretty viscous liquids, nothing like some of the positive displacements can, but light viscosities. Generally, a lot of these can handle very large solids. Some of them are quite poor in being able to handle solids. Some of them are built to be able to run dry, such as some of the vertical sealless pumps that we do a lot of. Some of them can handle large amounts of air, such as a vortex pump or a recessed impeller pump. Again, all of these charts are going to be available in our presentation, so don't worry about trying to write all this down or whatever. You may want to take a picture of it if you choose, but generally, centrifugal pumps enjoy a very good reliability. One of the biggest weaknesses of centrifugal pumps, if it's a sealed pump or a packed pump, is the ability to be able to keep that seal without failure over a long period of time. Moving on, again, a series of trade-offs. This is a video that I wanted you to see. I got it off of YouTube. I did not create this video. I'm not going to take credit for it. In fact, I'm plagiarizing the source. I think it does a pretty good job of explaining how a centrifugal pump works. So let's take a minute and enjoy this. Hopefully you can hear the sound.
Hi, I'm Adam. This is the Machine Tech video blog, and today I'd like to talk to you a little bit about the different types of centrifugal pumps. When it comes to pumps, most operators only care about inputs and outputs. How much pressure does the pump generate? How much flow does it deliver? How much power is required to run it? But maintenance people need to know a few more details about the inner workings of these machines if we're going to be on the hook to keep them in good running order. We don't have time to cover the specifics of centrifugal pump operational theory here, but it was the topic of a previous video. Just as a refresher, centrifugal pumps get their name from the way they impart energy to fluid. When fluid enters the pump, it comes into contact with the rotating impeller and is thrown outward by centrifugal force. It travels through a specially shaped chamber called a volute and exits the pump at the discharge outlet. All centrifugal pumps share this basic operating principle, but there are a few possible variations among them. There are 5 primary design elements to consider: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. There are a few special designs as well, but those will have to wait for their own videos. There are 3 types of impeller: open, semi-closed, and closed. The simplest impeller construction is the open impeller, which consists of nothing more than a few curved blade-like vanes equally spaced around a hub on the rotating pump shaft. Large, unrestricted fluid pathways allow this type of impeller to pump fluid containing mud, leaves, twigs, sand, sludge, spray paint caps, dead birds, you name it. And that makes them ideal for trash pumps or this pump, which actually came out of a wastewater treatment plant where it was pumping raw sewage. It was necessary to handle gritty slurries with soft solids. And it even has special chopper blades just ahead of the impeller to help break down very large solids. Ooh. If the vanes are mounted on a backing plate called a shroud, then the impeller is a semi-closed impeller. And if the vanes are sandwiched between 2 shrouds, then it's a closed impeller. Closed impellers are more efficient than either semi-closed or open impellers because the fluid is directed through very well-defined pathways. That means that more of the fluid is pumped out into the system and less of it is just recirculated around and around and around inside of the pump. Of course, the trade-off is that they can very easily get clogged with debris. Whichever style of impeller is used in a pump, it's mounted on a rotating shaft and needs to be supported by bearings inside of the casing in one of 2 ways, either overhung or between bearings. In an overhung configuration, the impeller is cantilevered on one end of the shaft and the bearings are offset to the other side. This configuration places the suction and discharge piping at 90 degrees to one another, with the inlet directly in front of the suction eye at the center of the impeller. This is why pumps with overhung impellers are more commonly referred to as end suction pumps. End suction pumps are abundant in industry because they're relatively cheap and easy to manufacture, but they do have one big disadvantage arising from the way that fluid travels through the pump. During operation, there's a zone of low pressure at the suction eye where fluid first enters the impeller, and a zone of high pressure at the outside rim of the impeller where the energized fluid is released into the volute chamber. This high-pressure fluid also has a leak path to the backside of semi-closed and closed impellers, which totally throws off the balance of pressure. The net effect is a constant axial force, or thrust load, pushing the impeller toward the suction inlet of the pump. You can compensate for this effect a little bit by installing beefier bearings capable of handling thrust loads, or drilling holes through the impeller shroud to allow for some pressure equalization. But neither of these are true fixes for the problem. A more effective solution is presented if the impeller is supported by bearings on both sides, called a between bearings configuration. Not only does supporting the impeller with bearings on both sides generally improve shaft support, it also means that many of these pumps can employ symmetrical closed impellers with double suction. Since there are identical low and high pressure zones on both sides of the impeller, this effectively eliminates thrust forces due to pressure imbalance. And this design has another key advantage. The suction and discharge piping are normally positioned parallel to one another on opposite sides of the pump, and the casing is split axially so that just by removing some bolts and pulling the cover off, maintenance technicians can access the rotating assembly inside the pump without removing the whole pump from the system. This axially split design is why pumps with impellers between bearings are more commonly referred to as split case pumps. Now, those are all pretty convincing reasons to go run out and get yourself a split case pump right now, but of course there has to be a disadvantage. Because the manufacturing processes and the sealing requirements for split case pumps are much more elaborate than for end suction pumps, they're also naturally more expensive. Next on the list of design elements is orientation, either horizontal or vertical relative to the pump shaft. Centrifugal pumps are usually oriented horizontally, but they can also be oriented vertically. Vertical pumps are used in plants where a reduced footprint and space savings are desirable. And you may also find one down at the bottom of a well or sump connected through a long line shaft to the driver above. This brings us to the mounting method of the driver, usually an electric motor. There are two options for transmitting rotational force from the driver to the pump, either frame mounted or close coupled. If the pump and driver are two separate units, as they are here, then the pump and driver shafts will need to be connected by some type of a coupling. Now, couplings come in all shapes, sizes, and styles. But one characteristic common to all of them is that they require proper alignment of the shafts, and that can be a very finicky process indeed. To help facilitate and maintain machine alignment, the pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame mounted. For large, heavy equipment and for all split case pumps, frame mounting is really the only way to go. A second option is the close coupled mounting method, in which the pump and its driver share a common shaft, with the impeller mounted overhung on one side of the driver shaft. In this case, there is no need for a coupling or any of the extra labor required to perform sensitive alignment procedures. However, since both the pump components and the driver components are supported on the same shaft just by the bearings in the driver, this mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps have one stage with a single impeller and a single volute chamber. However, some pumps have additional stages connected in series to help boost the pump's discharge pressure. The idea is that the first impeller adds energy to the fluid and then feeds it into the next impeller, which adds more energy to the fluid, then feeds it to the next impeller, and so on and so forth until the fluid is eventually discharged into the system. Well, there's your introduction to the different classifications used for centrifugal pumps: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. And that's it for today from the Machine Tech video blog. I hope you learned something.
Okay, so there's a number of things in there that were pretty interesting in looking through pretty basic information, but it gives you a good example kind of how a centrifugal pump works. Moving on, the life expectancy of any pump, whether it's a positive displacement or centrifugal, is largely dependent upon the proper selection of the pump. Again, there's all kinds of trade-offs going on in this thing as we choose what type of pump for what kind of installation, what materials we want to use, what, if it's a sealed pump, what kind of seal it uses, whether we want to seal this pump or a sealed unit. Those are all trade-off choices. And the life expectancy of that pump is largely dependent upon that selection and how it's installed into the system. If it's improperly installed, boy, you're going to have problems. You can make a pump live for 12 years, or you can kill a pump in 2 days, depending on how it's installed and put into the right type of system. Selection involves a lot of aspects, including piping configuration, what the overall configuration or available space is in the installation it's going into, what NPSH is available, that's net positive suction head, and we're going to talk about what NPSH is going forward, and what the fluid properties are. Are you pumping gasoline or are you pumping toothpaste? All of those All of those considerations must be taken into account, and you need information from your customers to be able to make a good selection. And they affect the performance and life of that pump as well as energy use through that whole period of time. When we're talking about centrifugal pumps, one of the most critical installation factors, number one, is getting a good, solid, level base plate for that pump to be mounted on. And then making sure that all of the piping, the inlet piping here and the discharge piping here, has its own support. We do not want to have all of this pipe hanging off of this pump, causing forces on this pump casing as it runs to go somehow out of alignment. That's a very critical thing. You also want to size your pipe on the inlet size, generally under 12 feet per second. I've seen cases where you keep a flow rate higher than that. A lot of people say they like to have it under 8 or 9 feet per second. Depending on the application, you may want to alter that some. Inlet piping should be roughly, have a straight run about 5 times what that diameter of that pipe is in a straight run to be able to get good, even, smooth flow into this pump. You don't want to have that flow being turbulated prior to even getting into the pump, because you want to fill all of those pump veins as this thing is running evenly. If you have a elbow very close to the suction side of this pump, for instance, the centrifugal, the weight of that water, it will, by centrifugal force, be forced largely along the outside of that elbow as that thing makes that bend, which means this side of the pump is going to get more flow, higher velocity flow of water coming into it than what would be here. In other words, as these veins are coming around, they're not going to be evenly filled because of that elbow right in front of the pump. And therefore, you're going to throw an imbalance on this whole shaft and this whole pump as it's trying to pump. It's doing more work on one side of the impeller than it is on the other. Additionally, you can use some flex connectors here, but even that only takes up so much misalignment. You want to make sure that this thing is aligned in a straight path axially, and it's not off on an angle side to side, and that the length is correct. When you take this pump casing out of here, these pipe connections should not move. I saw walking into a plant one time, a bunch of millwrights trying to install a pump, and they didn't have any pipe support on this thing, and the piping was out of line. It was a new installation, and they had a come along with a chain connected to a column, plant column, structural column, and they had this chain strapped across with a come along trying to get this thing into alignment with the pipe because the pipe was so out of alignment. I can guarantee you if an installation like that, that pump would not live very long, because you are forcing that pump completely out of line with that much stress. Additionally, I walked into a plant where they were having problems with seals on a pump, and they had a set up something like this, but up at the top here, there was an elbow, and there was 700 foot of pipe connected that going out to waste treatment. And all along that pipe, they had rollers supporting that pipe. So the pipe was supported vertically, but there was nothing to keep that. There was no support here. There was nothing to keep that whole pipe, 700 feet of it, from moving. And believe me, when you pressurize a pipe that long and you have pressure fluctuations in that pipe's going to move. So dynamically, as this thing ran, it was tugging on this pump, causing everything to go in and out of alignment. So again, pipe supports, correct pipe diameters, correct pipe length of straight pipe prior to the suction. The suction is much more important than the discharge side is. And I think that covers a lot of the pipe installation concerns. Again, a good solid base plate that's mounted down. I went into a plant one time and they were having seal issues again. And we were up on a mezzanine on the second story, a steel mezzanine, and the pump wasn't very well supported. And we had a laser shaft alignment tool hooked up to the pump shaft and the motor shaft. And as a person walked around the pump, the alignment changed. This was the pump off, motor off, sitting there with a laser alignment on it. Just as you walked from one side of the pump to the other, the alignment would change. So how in the world would you ever be able to maintain any kind of positive alignment between a motor and a pump shaft if your base isn't proper, if it's not correct? So the installation is extremely important, and there's a lot of things to look for. Moving on a little bit here, pump considerations. When a centrifugal pump runs, it's creating flow in the system by creating a difference in pressures. The pump is designed to add energy into the fluid being pumped, and if it can, it's going to influence enough energy to be able to create flow. If you, however, create too much resistance to that flow, whether it's on the suction or the discharge side, the pump can't overcome that amount of resistance. That happens on positive displacement or centrifugal, but it's very cumbersome on a centrifugal pump. So that pump's going to create enough pressure differential to be able to overcome that resistance if you can. If you can imagine a pump that's capable of going, say, to 40 PSI, pumping into a header that's already at 50 PSI, which is being pressurized by other pumps, you're not going to get any positive flow. In fact, you're going to get negative flow. You're going to get flow back through that pump to the source unless there's a check valve to stop that reverse flow. That pump that's capable of doing 40 PSI is not going to be able to push into a 50 PSI pressurized line. Makes sense. So when flow is in a system, there's always a resistance to that flow, whether that's friction moving through a piping system. You know, that one installation I talked about that had 700 feet of pipe, to be able to get a certain amount of pressure at the other end of that pipe, you have to overcome all of that resistance in that pipe. So you have to size that pump to be able to have that much pressure at the pump side to be able to get certain amounts of pressure on the discharge side of that pipe. Some of the other resistance to flow, whenever you change directions or accelerate the fluid from one state, one flow rate to I guess I shouldn't say a flow rate, but a velocity rate to another velocity rate, in other words, a smaller size pipe with the same amount of flow going through it, you have a change in acceleration. That's a relatively small loss, but it is a loss to consider. Of course, in a system, whether you change the fluid elevations from where you're pumping from and pumping to, that is a resistance to flow. And any existing pressures in that system, such as a pressurized header that I was talking about, a 50 PSI pressurized header, you have to have enough pressure on the pump side to be able to overcome that resistance. As it runs, a pump creates a low pressure zone at its inlet, which induces flow into the suction piping and into the pump. And if we were look at a pump itself, you see suction coming in, picking up by these impellers. It's then being circulated around the outside of this volute until it comes over to this area, which this is the cut water that he was talking about in that video. And that basically separates the flow off to go out the discharge. Now, when we design one of these centrifugal pumps, this pump may have, if this is a 3x4/8, for instance, which means it has a 3-inch discharge, 4-inch inlet with an 8-inch maximum impeller, we may trim this impeller for proper performance to, say, 7 inches, which means that there's going to be even more space between this cut water and the impeller than normal. Well, what happens in that particular case is that cut water becomes less efficient, and there's more water that recirculates back inside this pump around this volute. So we lose some efficiency, and it is, unfortunately is a loss that's pretty normal in pumping systems. When you look at a performance curve, and we're going to start talking about curves here pretty quick. When you look at a performance curve, a performance of a pump has a pretty fixed and predictable and repeatable performance given a certain set of resistance. And it's all dependent upon what size impeller we choose, what rotational speed that impeller is running at. It's all about tip speed of the impeller itself as far as how much pressure it can create. And by pressure, that is what overcomes the resistance. And when we talk about pump curves, you're going to see that all of the pump curves are in feet of water rather than in PSI. Of course, people are accustomed to talking about pressure per pounds per square inch pressure. So it makes people confused. Your customers are probably going to say, well, I want 40 PSI. Well, with different types of fluid, the pump doesn't know the difference. It is a simple device that's slinging fluid. If you put a heavy fluid into it, it takes more energy than it does a lighter fluid, such as gasoline. So gasoline has a specific gravity of about 0.78, meaning it's 78% lighter than water. Specific gravity of water is 1. Hydrochloric acid may have a specific gravity of 1.6, means it's 60% heavier than water. So if you move 400 gallons per minute of gasoline, it's a heck of a lot easier to move 400 gallons of 78% lighter than water fluid than it is 60% heavier hydrochloric acid. So the pump itself doesn't know, and our curve doesn't know what kind of liquid you're going to use on it. So we convert to feet of water. And part of that conversion factor is going to be explained in how we talk about curves and how much energy specifically it takes to move that heavy fluid is going to be quite different. And we talk about energy. Energy is extremely important when we talk about pumps because it's estimated that 5% of industrial energy goes to operate pumps. The pumping systems account for nearly 20% of the world's electrical energy demand and range from 20 to 25% of energy usage in certain industrial plant operations. In fact, I'm pretty sure that in some that I've seen, it's higher than that. You may walk into a paint shop and it may have 300 pumps running in that paint shop constantly. And that is a very significant part of their energy consumption. Energy consumption is estimated, of course, it's going to vary on the type of pump and how often it's operating and all that kind of stuff. But energy consumption oftentimes is as high as 90% of the total cost of owning that pump, including purchasing it. So how efficient that pump is extremely important in design. And oftentimes it's an overlooked part of the design. We were talking before about different types of fluids and being able to convert from feet of head to PSI. These are your formulas for that. When you have reference in feet of head, that's if you knew what PSI you wanted, say 40 PSI, you would take that times 2.31 to be able to get to the number of feet of head. Well, what is that telling you? 2.31 times 40 PSI, I believe, is about 93 foot of water. If you had a column of water that was 93 foot tall with no existing pressure on it other than atmospheric pressure, at the bottom of that column, there would be 40 PSI of pressure. So what we're doing is equating that basically to a feet of water column to be able to get to feet of head. And that's what our curve is going to be rated in. So PSI is equal to feet of head times 4.33 times specific gravity is another way to get to that PSI value. In other words, if you knew that you had 60 or 93 foot ahead times 0.433 times your specific gravity of that fluid, assuming right now it's water, that would equal to about 40 PSI. So Hopefully this helps you a little bit understand why a curve, performance curve, is in feet of head. When we start looking at curves, this is going to be something that you're going to see. This pump does not know where it's going to operate on this curve. This pump is going to try to follow that curve as long as you give it enough fluid. Anywhere on that curve is where this pump's going to operate. And on the left side of this curve, you're going to see that rating in feet of head. And across the bottom, you're going to see the flow rate in terms of flow in generally gallons per minute. If it's a metric curve, this may be in cubic meters per hour, and this may be in meters, or potentially maybe even in bar or atmospheres, which is what bar stands for. Also on the pump curve, you're going to see different impeller trims on a centrifugal pump curve. For instance, if we had a 3x410 pump, the maximum impeller diameter may be a 10-inch diameter impeller on that. And this is what that pump would do if we had a 10-inch impeller in it. If we trim that impeller, which we generally do, to a 9-inch, that would be approximation of your curve. And there's always some variance in curve performance, albeit small, because of the clearances that are within that casing. Remember, I talked about recirculating water from the low pressure side to the high pressure side, where the cut water is at. There's always going to be some losses that are not 100% consistent, depending on what your spacing of gaskets are and specific clearances. And then if you had an 8-inch impeller, if this same pump were trimmed at 8-inch, this would be an approximation of that performance. So when we actually look at a pump curve, what you're going to see is a lot of information here. So we saw this one has a maximum diameter of 8.37 5-inch impeller. We actually call this a 3x4-8, which is the model number here. This CL in our nomenclature means that it's a centerline discharge, probably an ANC pump. 3-inch inlet, 4-inch discharge, 3-inch discharge, 4-inch inlet, and a maximum nominal 8-inch impeller, where actually this pump can do about 8.375 maximum impeller. If we were to look at this curve, you're going to see dashed lines coming down here. These are horsepower load lines. And if you were to have a pump with this size impeller and it was running here, you would know that this is consuming somewhere around 7.5 horsepower with water at that particular point. All of these curves basically are treated in water. If we were to run farther out on the curve, in other words, less resistance, more flow, we get out here somewhere around 475 gallons a minute at about 55 foot ahead, 56 foot ahead or so. And it would be somewhere around 10 horsepower of load. So the more water flow, even though it's less pressure, the more the horsepower load, the more the horsepower demand on that pump is. There's an interesting area right here. This is called the BEP, or best efficiency point. And in this particular pump, that's about 69.5% efficiency. And this is the point on the curve where that pump is running the smoothest, where it's getting a nice inflow, it's got a nice discharge, there's not a lot of turbulence in that pump. It's the highest efficiency operation of that pump, 69.8%. So at that particular point, down at the bottom of this curve, we have what's called an NPSR rating. And NPSHR rating stands for net positive suction head required of this pump. To be able, in other words, that's what pressure on the inlet side of this pump needs to be able to fill all of those impeller vanes full of fluid without any kind of air pockets or cavities or voids. Okay, so following this NPSH curve, out on this curve, we see that it's about 5.5 feet is required at that flow rate of NPSH. And we're going to talk more about NPSH, so don't get too freaked out by that yet here. So the other lines that we see here, all of these green lines coming down, these are efficiency lines, but they're there in case we trim this pump. Okay, so if we trim this pump to something along this lines right here, let's say that's a 7-inch impeller, where's your best efficiency point? It's about right here. So the best efficiency point falls back to about 400 gallons a minute with a 7-inch impeller, as opposed to 435 gallons a minute with an 8-inch impeller, give or take. And so that efficiency, best efficiency, basically you could draw a line right along here so that if you trim that down to a 6-inch impeller, again, you'd know about what your efficiency is, you know about what your horsepower load is, you'd know what the NPSH required to be able to fill all of those impeller vanes with fluid and not have cavitation. So there's a lot of information on this curve, and a lot of it's very important to a pump design standpoint. Jumping ahead here, the Hydraulic Institute suggests, and the Hydraulic Institute is kind of the governing body for the pump industry. It's an association of pump manufacturers and pump users that was formed to be able to help pump manufacturers and pump users talk in the same language and have the same standards and get the best performance out of pumps. They always recommend that a pump be operated between 50% and 120% of best efficiency point. So in this particular case, if the best efficiency point was an 8.375-inch impeller, that pump should always be operated between 217 gallons a minute on the very bottom side and 522 gallons a minute on the top side. What does that stand for? The 217 is the 435 times 0.5. The 522 is 435 times 1.2, or 20% over. So again, we want to operate within that window. Oftentimes you'll see manufacturers stop their rating lines somewhere out here, which is what they consider the minimum flows for this pump. They wouldn't want you operating for any kind of period of time. And in fact, when you get over here in deadhead, which is what we call that, where you've created so much restriction that there's little or no flow, things really become erratic. We have a curve oftentimes out here, but the predictability of that curve in this area is just about zero. It's just not sure what's going to happen in this area. So it's there to be able to try to help you diagnose, and we'll talk about deadheading a pump later, but it's there to help you try to diagnose a pump, because generally in a system, the only point you know that it's operating on this curve is at zero flow. When it's absolutely no flow, that's about the only point in this curve in a system that you know where it's operating at. So we put it there to give you some kind of an approximation from a troubleshooting standpoint, but you never want to operate your pump on any kind of regular basis below about 50% of flow, which is 50% of BEP, or best efficiency point, which is 217 gallons. So it's somewhere in this ballpark right here. You never really want to be operating back here. And again, it's all resistance to this system that determines where you're going to operate on this curve. So we talk about a system, and we could create, by knowing what restriction we have in a system, we could create what's called a system curve. And that pump's going to operate wherever that pump curve and the system curve cross each other. And that's where the pump's going to operate. However, the system curve is pretty dynamic. It's generally changing. It might have filters that get dirty. You might have nozzles that plug up. You may have valves that are partially closed at times by operators. Whatever changes happen in that system determine how much flow you're going to get out of that pump and where that pump's going to operate on its curve. We've had systems where they were having seal issues, and come to find out that for whatever reason, they may shut off a couple pumps at night and just leave one circulating. Well, the problem with that is the system was built for maybe 3 pumps in unison pumping into the same header. And with one pump only operating, there's nowhere near enough resistance. So there's a lot more flow. The pump is running out off its performance curve, way out past best efficiency point. Well, some strange things are going to happen inside that pump that we're going to talk about that would happen as that pump runs out on that curve. But the important point at this point right now is that the actual operation point is going to be determined by where that system curve is and where the pump curve is. And as long as you get as much flow as it needs into the pump, in other words, you're not starving the pump on the input side, it's going to follow that curve. So this is one system curve. Okay, so we know that as flow goes up, there's more resistance to this curve. I can tell you by looking at this curve right now that there's no effective lift in this curve. If we were lifting, like say 10 feet in the air, this pump over here at zero flow would be up at 10 feet because it would take that just to start getting some flow. So that curve would be a little different if say we were lifting 10 feet or 20 feet, it might start off here and come up. But you could create a system curve based upon how much resistance that you know in the system or calculate in the system. And then if you overlaid that with your pump curve, this is the original system curve, you could tell about where that pump's going to operate at. It's going to be somewhere in this ballpark pretty accurately if we've calculated it accurately. And that's where the pump's going to operate. However, if you take and start closing off a valve and throttling that valve back, it's going to change that system curve. So our system curve has changed. Our flow rate, therefore, has changed. Remember I said when we had 3 pumps running in unison pumping into a header that we had calculated that we would have so much flow in that system. Well, if we shut off those other pumps, what we're doing is we're creating that open system, and that pump is allowed to run way out on the curve, which is generally a very bad thing. We're going to get out in areas where we're going to get cavitation. We're going to get out in areas where we have a lot of shaft movement and bad things going on in that pump. So when we look at a centrifugal pump, this is normal. It starts building pressure as this flow starts coming around this casing of the loop and coming over here where it really reaches its largest pressure rating typically on the discharge side. Well, if we created a situation where we have too much resistance on this pump, in other words, the valve up here is throttled too much, there's too much back pressure on it, the filter is dirty, filtration may be coming out of this thing. What happens is we created too much resistance here. The pressure is really building here. It can't get out the flow rate that it wants. Remember, a pump is a dumb thing. It's just trying to sit there and spin and create that flow. And it can't get out this discharge side fast enough, and it starts recirculating here back across this cutwater back to the low pressure side. It's the only place that it can go. So what happens here is this pressure is built up on this side of the impeller. All of a sudden it forces this impeller this way because this is low pressure side and this is high pressure side. There's a big differential between these two sides of the impeller. It forces this impeller this way. Well, the problem is this pump is spinning, say 1800 RPM or 3600 RPM. All of that shaft is being forced this way and bending that shaft on a continual basis. It's forcing that pump that way. On the other side of this, if we have too little resistance, say with that system that we were designed to have 3 pumps running, but only 1 running, there's going to be very little back pressure. So this side of the pump is going to have very little pressure on it. It's basically just flowing out of there, but we're building pressure on this side. And therefore there's a pressure differential across this impeller, and it's going to force this impeller this direction out of balance this direction, creating that shaft to deflect the other way. So if we were to graphically look at that curve and we looked at the radial force, the amount of that force on that shaft to bend one way or the other, we could plot it out that it would look like something like this. At best efficiency point, there's very little radial force. That pump is running very smooth. There's not a lot of side force one way or another on that impeller. Therefore, the bearings and the shafting and all that stuff are running extremely smooth in that pump. However, if we get either way too far on that curve, those radial forces go up. It causes that pump shaft to bend one way or the other. We start getting into areas of possible cavitation because NPSHR may be too high for the system to be able to meet it. Bad things happen. And one of the first things that happens as we're running off the curve on either direction, if it's a sealed pump, is we may have enough shaft movement that we're going to cause that mechanical seal to fail prematurely. A mechanical seal really depends on smooth operation for the faces to be able to come together. Typical mechanical seal has one rotating face that rotates with the shaft and a stationary face that rotates with or that's stationary in the pump casing itself. And those two are riding on each other. It's a matter of one rotating and one stationary, and it's those two faces that close. If you start getting too much shaft movement, those faces can pop open momentarily as that shaft is being bent or that shaft is moving back and forth, so that you can start getting those faces to bounce. And when they start bouncing, water starts leaking out or fluid starts leaking out of that pump. So that shaft, that shaft mechanical seal, where that shaft comes through the pump from the motor side, that mechanical seal there that's installed in the pump begins to fail, begins to leak, and your customer's not going to be happy because they've got a pump that's leaking. If we were to look at the shaft being here, when we start getting off on that curve one way or the other, we get a radial force that causes that shaft to bend, to deflect one way or the other. That's why the Institute of Hydraulic Standards says we should operate between 50% and 120% of BEP to try to minimize that shaft deflection. And if you look at the effects on the seal, this is in this particular graph here, this is the stationary part of this seal. This is connected to the pump casing that would be up in this area here. And this is the part that's stationary to the shaft. It's rotating with the shaft itself. So it's a rotating side of this seal. And the two faces here running on each other is what keeps that pump from leaking. And if you get the shaft deflecting, you're causing this seal. Remember, this thing is turning 1,800 or 3,450 RPM or whatever the speed of that pump is. And the stationary or the rotating part of this, because of that deflection, has to keep adjusting back and forth. And there's generally a spring on these things to try to help keep those faces closed. But you're causing this thing to move so much that sometimes it just can't. Another phenomenon happens that on the inside of this rotating part of this seal, there's an O-ring that makes that seal between the stationary and this shaft. And because that thing's wobbling back and forth, this is a shaft sleeve itself, which would be basically underneath this seal. You can have what's called fretting corrosion that causes that wear ring to actually eat into the metal shaft sleeve. And sooner or later, as that eats into it, even if these faces don't open enough to cause leakage, it's going to start leaking across that shaft sleeve fretting area. So shaft deflection is bad on mechanical seals. It's much more forgiving on a pump that doesn't have a mechanical seal or packing in it. It's much more forgiving to be able to have some shaft deflection, and we can kind of accommodate for it. But again, operating too close to deadhead, operating too far out on a curve will cause this shaft to deflect one way or the other as this pump is spinning. I'm going to open it up for questions at the moment, so I'm going to unmute you all. And if you have any questions, if you would, if I can find the unmute button. Bear with me for a second. Okay, you're all unmuted. Anybody have questions? Okay, I had to mute you all. Somebody had maybe computer speakers going as well as a phone or something there, causing a feedback situation. But you can, if you have some questions, you can put them up on the notes column. I think Lisa Wallner, our marketing director, is kind of managing that, and hopefully she can let me know if there's any questions going forward. I don't see any notes at the moment, so.
You can all, can you hear me, Dan? You can all each unmute yourselves individually as well, I believe. That's why I just did, to ask your questions.
Good. Any questions? We've covered a lot of ground already. Let's move on. So we talked about shaft.
Oh, I had a question. Sorry.
Yeah,
Sorry.
go ahead.
I'm trying to catch you right as you're turning the corner here. Sorry. We can go back to that. There you go, on that slide with the deflection and the radial force there. So over time, as we're looking at pumps in this application where they're getting this excessive radial force, we assume that eventually at some point these bearings are going to also show wear, and regardless of a new seal, a new shaft, if these bearings aren't addressed, you could continue to see, you know, reduced life, seal life, just because the bearings are wearing out as well.
Oh, absolutely. No question about it. The first thing that's going to fail is probably the mechanical seal. For obvious reasons, mechanical seal, these faces could bounce open, or that fretting corrosion could cause leakage underneath the seal. But you know, there's certainly excess forces that pump wasn't designed to be able to handle in this operation, and some of it can be a changing force, which is to some extent even worse. You know, a ball bearing can kind of accommodate itself if the force is fairly consistent. But generally, these type of instances where we're out on a curve or at deadhead, it is a fluctuating, and not only do we get a radial force on this thing, but quite often there's a thrust force that changes as well. And that's because all of that flow is trying to relieve itself from the high pressure side where it can't go anywhere, for instance, back to the low pressure side. So it's going to force that shaft. If I go back to this drawing here, it's going to force this shaft to move in and out this direction as well, to try to get some of that high pressure fluid that's out here on the fringes of this volute back across the front side of this face back to the suction, which is the low pressure side. So it's going to force this impeller not only to move radially like this, but also thrust load back and forth towards that low pressure side too. So absolutely, the bearings would have a premature life, but the major complaint you're going to find, especially initially, is going to be failing seals, because those seals in a bad installation or bad operation condition are going to fail prematurely.
Thanks, Dan.
You bet. Any other questions? There's a lot going on inside this this casing, and when you create that back pressure, and we're going to talk about cavitation, when you create this thing to have all of that backflow, could you imagine how much turbulence you're causing inside this casing? This casing, you know, a 3x4/8 that we were talking about there, 435 gallons a minute, 435 gallons per minute at 8 point, let's say 3-4, whatever pounds per gallon, is 2,400 pounds of fluid that is moving through this casing per minute. And if you're forcing 30% of it back across the front side of this impeller, what is that? That's 750 pounds of fluid that you're trying to relieve. There are going to be bad things that are going to happen inside this casing because of all of that movement, all the turbulence and stuff. And again, we're going to talk about cavitation, and that's going to be a major part of that conversation. So again, important point, you try to operate between 50 and 120%. Let me go back to the curve for a second too. There's one thing I wanted to mention while I'm there. If we were looking at this curve, because I know that we want to operate between 50 and 120%, which is somewhere in this ballpark right in here, right? Well, where am I going to want to pick this pump? Of course, I want to get close to BEP, but the problem is that if I pick it at BEP, I've only got 20% margin for error on this direction, and there's always going to be a change in the system. First of all, engineers generally say, okay, if I want 700 gallons a minute at 40 PSI, I'm going to tell my pump supplier that I want 800 gallons a minute at 50 PSI, so I know I have enough. So I've already oversized this pump. So when that pump comes into place, it doesn't know it was oversized. It doesn't know that it shouldn't be, or should only be producing 700 gallons a minute at 40 PSI. It's trying to produce 800 gallons a minute at 50 PSI. So we're already forcing this thing to move off of this curve just because the design was not exactly what we thought we wanted in that system. Furthermore, as people construct a system, you know, they may, for whatever reason, they may have more resistance or less resistance in this system than they ballparked. And it's all kind of estimating as you're building the system. So even though we say we want 700 gallons a minute, or in this particular case, let's say 400 gallons a minute on this pump, the reality is that it's probably not going to run at 400 gallons a minute. The reality is that it's probably going to run at 300 gallons a minute or 500 gallons a minute or somewhere other than 400. The ability of us to accurately size this pump from an engineering standpoint, a pipe system engineering standpoint, is good, but not exact. Unless they really went to great lengths to try to pick it. If they say they want 400 gallons a minute, it's probably not going to operate at 400. But the bet is it's going to operate somewhere else. So when I'm picking this pump, knowing that I would like to be close to BEP, but I only got 20% margin on this side, and I got 50% margin on this side, what am I going to do? I'm going to say I'm going to pick, because of those variances, I'm going to pick this pump ideally somewhere probably around 85% efficient. So I've got 35% margin on one side to go to 50%, and I've got 35% margin on the plus side to go to 120%. 85 plus 35 is 120. 85 minus 35 is 50%. So ideally, I'm going to be looking for a pump that's somewhere a little bit left of best efficiency point. That is the most opportune point to be able to give myself the widest margin as a pump supplier, pump manufacturer, knowing that it's probably not going to operate just exactly as it was designed for. Does that make sense? Any questions on that? It was a good question on the bearings, by the way. Appreciate it. Okay, so let's start talking about net positive suction head. And this is one of those vernaculars that I hesitate using, but it's the most accurate way and the way people, pump manufacturers and pump people, know what to talk about. Basically, it's the amount of pressure that fluid has at the inlet of the pump. And it has to have enough pressure to be able to fill all of those pump vanes as this pump is spinning at 1800 RPM or 3450 RPM or whatever RPM it's spinning at, so that we don't have any voids. We're filling all those pump vanes properly as this thing is spinning. And there's two expressions, which is NPSH-R, which is what's required of the pump, and that's something that the manufacturer determines on his pump curve, and it's on his pump curve. And there's NPSH-A, which is what you measure as that pressure available in the system. And again, manufacturer is going to tell you what NPSH-R is. If you don't have enough NPSH-A in that system to be able to at least meet NPSH-R under any condition, you're going to have cavitation. You're not going to fill those veins properly. And cavitation is a bad thing. And we're going to talk about why cavitation is a bad thing. Again, we start talking about vibration in the system and bad things that happen. All of that disturbance that's happening inside the pump. But to calculate NPSH available in the system, it's a matter of barometric pressure, how much atmospheric pressure there is pushing down in the fluid that's going into this pump. All fluids try to evaporate off. Water, even at 70 degrees, evaporates off. So that fluid is trying to evaporate. It's basically working against the atmospheric pressure, pushing down on it, trying to evaporate. And it's a term that you can look up on a fluid chart, and it tells you what that vapor pressure is for a certain fluid. On water, we know that water vapor pressure equalizes with atmospheric pressure, generally at sea level at 212 degrees, because that's when water turns to steam and boils off. So vapor pressure, we know, is 32 feet or 33 foot, which is what typical atmospheric pressure is at sea level. And we know that at 212 degrees, where it starts to boil, it equals what that atmospheric pressure is. That's what boiling is. If you're at 7,000 feet, that atmospheric pressure is going to be less, and we're going to talk a little bit about that. So the other thing that we have to include into this NPSH calculation, besides the barometric pressure and the vapor pressure, would be whether we have a suction lift or head condition. Is that liquid level that pump is drawing from, the liquid level itself, is that above or below the pump? Generally, it's above for a centrifugal pump, but in a case of a self-primer, it's below very often. Self-primer is typically mounted above liquid level, so therefore we're already losing some liquid, some head, trying to get that water level up to the pump before it even comes into the pump. And the other thing that comes into consideration there is friction, pipe friction. If we have a pump mounted right underneath the tank and it's got 3 foot of pipe, it's generally not too much a concern as long as that pipe is sized properly. But if we have a pump that's mounted, say, 200 feet away from a tank, and we want to move 400 gallons a minute through that pump, which means we need to get at least 400 gallons a minute into that pump, is there going to be so much friction loss in that 200 feet of pipe at 400 gallons a minute that we're not going to get enough flow into that pump? So we have to take friction losses of that pipe at that flow rate, or hopefully greater, into account when we start figuring out how much NPSH we have. And this is kind of a thing where a lot of people get lost. So, but it's really a simple calculation. The atmospheric pressure is pushing that water into a pump. And 1 atmosphere, or bar, is about 101.33 kilopascals in metric terms, 14.7 psi in pressure terms. This is at sea level, or 33.9 feet of water column at sea level. However, if the system that we're talking about is at 7,000 feet or 2,136 meters above sea level, average atmospheric pressure, and atmospheric pressure changes, but average atmospheric pressure at that point is 78.19 kilopascals or 11.34 psi. So we've dropped from 14.7 psi to 11.34. So if you're selling somebody a pump in Mexico when they're up in at Mexico City or Puebla, which is probably pretty close to 7,000 feet, or if they're in Denver, Colorado at 5,000 feet above sea level, we have to know that that starting formula for NPSH, the atmospheric pressure of the atmosphere pushing down in that water, is greatly reduced. We only have about 26.2 feet of water column equivalent of atmospheric pressure that we're starting from. And all the other things that we talked about, there are generally losses that create this NPSH calculation. This is the chart that I talked about as far as vapor pressure. And this is temperature of water, and this is based on water. And it tells you what the specific gravity is, which changes a little bit as temperature of that water changes, because water expands a little bit as it starts getting closer to boiling. And then the vapor pressure in feet at that temperature. So right here at 212, we're at 35.353 feet. We know that that is boiling because it's greater than the 33.9 feet of atmospheric pressure at sea level. So you can use this chart. So if you're pumping 140 gallon or 140 degree water, let's say you're at sea level, you would take that 33.9 and minus 6.76, which is, what is that, about 25, ballpark 25 foot left over for NPSH available. So after this part of the calculation, you know you got about 25 foot available of NPSH, which is the 33.9 minus that 6.76 at 140 degree water. So then what other things that you need to take to effect? If the water's again above this pump, you can add the distance from this liquid level here to the center line of the pump onto that number. So let's say this is 3 feet above this pump. If you knew you had 25 foot of NPSH with that other calculation of the atmospheric pressure minus the vapor pressure, you now have 28 feet of NPSH available because we've added this 3 foot above it. If you're talking about a self-priming pump that has the liquid level down here, say 10 feet, you need to subtract that 10 feet of lift from that 25. So now you've only got 15 foot of NPSH available. That atmospheric pressure is still trying to push that water up that pipe column. Okay. So we now have accommodated for the difference of the liquid level of the source to the center line of the pump in our NPSH calculation. The next thing, then this is going to vary by system, is your piping. You know, if you've only got a few feet of pipe and it's the same size as the pump inlet or larger, generally this is going to be so low that you don't need to worry about it too much. However, if you've got 200 foot of pipe and it's the same size as the inlet of the pump itself, you may have a lot of friction loss to account for. And there are friction loss charts and programs available for you to be able to calculate typical friction loss through a certain size pipe. I have a spreadsheet that I will make available for you if you want. It's called, I call it a technical reference chart. And it's got the vapor pressure charts and it's got friction loss charts, how to calculate how much flow across a weir. It's got a lot of different things on it. It's a very large spreadsheet, and I'll make that available to you if you send me your email and request it, or send me an email and request it. But this is something you're typically going to pull off of either a pipe sizing program, and there's a couple that are available as apps that are inexpensive or free, or off a chart somewhere, perhaps in the back of a pump manual. Somewhere or another, you should be able to figure out what the friction loss through piping is. So you would take, again, all of those factors, the atmospheric pressure minus the vapor pressure. Again, this is just measuring how much pressure is coming into this pump, plus or minus the liquid level, minus whatever friction loss that pipe is. If you have a dirty pipe coming into this thing, it's scaled, it's got a lot of mineral deposits or whatever build up into it, you can no longer necessarily trust a friction loss chart. You may have a suction strainer, and this can be a huge problem on pumps. You may have a suction strainer trying to keep big solids from coming into this pump on the suction side of this pump, but guess what? It got filled with junk and now it's dirty and now it's creating a big restriction to that flow. And something you thought was very low loss, all of a sudden is a large loss. So if you have a suction strainer, that can be a great thing, but it can also be a very bad thing on a pump, because all of a sudden we can starve that pump, not fill those pump veins, and cause cavitation. Other concerns to NPSH would be perhaps viscosity. Viscosity affects how easily that flow goes through that pipe. So there are some other concerns, but in general, it's atmospheric pressure minus vapor pressure plus or minus the liquid level minus the friction loss. And that's going to get you darn close in most cases. Next, we're going to talk about cavitation. Okay, so if we don't fill those pump veins well enough, what we get into is an area where this pump is trying to pump water that doesn't exist. And we're going to cause cavitation on the suction side of this pump. And basically, and I've got a video that I'm going to show you next frame that explains cavitation quite well. Basically, it is a vacuum bubble that's created by low pressure that all of a sudden collapses. And that collapse is so violent that it can destroy metal that's close to that collapsed bubble if that metal's close to it. That's how violent a collapse it is. And that's why cavitation is so damaging. And this one, again, this is stuff I found on YouTube. I think it's a pretty nice video. The next one I think you're going to like even more. Next one I think is somebody did it in England or something. There's a pretty good accent on it, but hopefully you can get something out of it. So without further ado, let's go to this video. Well, for whatever reason, it's popping up on the screen, but we'll do it here.
Now the first thing that's going to happen is we'll have it cavitating right here at the valve. Got cavitation right here at the valve. If I continue to close the valve, I'll move the cavitation right in there to the eye of the impeller.
Those bubbles that you see are cavitation. This one
There's some noise. Things don't look so great. Flow meters dropped way off. Makes it pretty easy to see inside of there what's going on. What's it look like you see it?
Because of that volume.
Most of the time, first time somebody sees that, they say, well, that's air. Okay. Looks like an air leak. It looks like you're seeing bubbles of air in there, right? But I didn't open up any of these air bleeds. There's two ways you can boil water, right? Take a pot of water, put it on the stove, turn on the heat, 212 degrees Fahrenheit, the water starts to boil, you got steam coming up off of it, okay? The other way you can boil water is by lowering its pressure. The way we lower the pressure of the water is by increasing the velocity. As the velocity of the liquid goes up, the pressure goes down, and the liquid can no longer stay in a liquid state. It's going to flash to vapor. And that's what we're doing. I've got about 69, 70 gallons a minute going through an 1.25 inch opening. As I start to close that opening down real little, I've got to have the liquid has to go faster and faster to get through that real small opening. Okay? So as the velocity of the liquid goes up, the pressure goes down. The liquid can't stay in a liquid state, it flashes to vapor. As I get to the eye of the impeller, I get on the discharge side of this pump, there's no restriction. So all that liquid slows back down and those vapor bubbles implode back into liquid. And that's where the destructive force of cavitation is when those vapor bubbles implode back into liquid, they give an energy discharge that's been measured between 80 and 110,000 psi of energy release. Okay? The tensile strength on a ductile iron impeller is nowhere near that. So what happens is you start to blow away chunks of metal at the eye of that impeller. It's pounding away at the eye of that impeller, 80 to 110,000 psi, so the vapor bubbles implode back into liquid. You get an impeller where the tips of the impeller look fine. There's nothing wrong with the tips at all. But if you look in there at the eye, you got little chunks of metal blown away at the eye.
Okay, so you can tell from that demo or that video that what we're really doing in this sense is we're restricting the flow into that pump so much so that cavitation is flowing into that pump even before it gets to the pump. And this next video, I really like this video quite a bit, but it really gives you the details of why cavitation happens and what it does. And I really love, I got to tell you, the microscopic photography that's done here, I think is just phenomenal. So let's take a look at this.
Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this series, we are going over the phenomenon of cavitation in water and its consequences. What is cavitation? Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. Such cavitation bubbles are formed mainly in locations within the liquid where the static pressure becomes smaller than a liquid's vapor pressure. The phase diagram of water shows if water is in its gaseous, liquid or solid state, depending on temperature and pressure. The horizontal axis of a diagram represents temperature, while its vertical axis shows pressure. The vapor pressure curve is part of a phase diagram. It indicates at which pressures and temperatures water evaporates from liquid to vapor or condenses from vapor to liquid. At a constant pressure of 1 bar absolute, water in its solid state, which is ice, melts to liquid water at a temperature of 0 degrees Celsius. Keeping the pressure constant at 1 bar absolute, liquid water evaporates when the temperature is increased above 100 degrees Celsius. Evaporation of water is not only possible when the temperature is increased at a constant pressure. The other possibility is to keep the temperature constant and reduce the pressure below the vapor pressure. Water can evaporate and condensate at temperatures below 100 degrees Celsius if a static pressure is low enough. This is exactly what happens when cavitation occurs. Bubbles of water vapor form when the pressure in a certain location decreases below the vapor pressure. The vapor condensates back to liquid once the bubble has reached a location with a pressure above the vapor pressure. But how is it possible that the pressure becomes very low in certain areas of a fluid? Let's have a look at an example for illustration. If objects, such as blades of a ship propeller, are moved through water, there is a higher pressure on the side facing the flow and a lower pressure on the opposite side. On other edges exposed to the flow, low pressure can also lead to cavitation. The bubbles collapse as soon as they reach an environment with a pressure above the vapor pressure. When pumps circulate water through piping systems, cavitation can occur where the pressure is lowest, at the inlet of pumps and in narrow pipe sections. If the pressure at the inlet of a pump is low and approaches the vapor pressure, cavitation can occur at the pump impeller as we have seen it at the ship propeller. The pump can deliver less water because the cavitation bubbles occupy a part of the cross-sections where the water should flow. damage from collapsing vapor bubbles will be shown later. The same amount of water per time flows through the pipe with a large cross-section as through the narrow cross-section. Therefore, the velocity is higher in the narrow part and the static pressure is lower. The pressure is especially low at the exposed edge at the inflow side of a narrow part. We show a detail of a phase diagram of water, which allows to analyze the situation in a narrow pipe section. The temperature of a flowing water can be 20 degrees Celsius, which is a vertical line in the diagram. It crosses the vapor pressure line at an absolute pressure of 2,300 Pascal. As long as the pressure is higher, water remains liquid. If the absolute pressure decreases below 2,300 Pascal, water evaporates. The colors in the left visualization correspond to the colors indicated on the vertical axis of a phase diagram on the right. Upstream of a restriction, the static pressure is well above the vapor pressure. The static pressure in the flow decreases as the flow reaches the narrow pipe section. In our example, the pressure at the exposed edge is below the vapor pressure. Consequently, water evaporates and cavitation bubbles are formed. The low pressure at the exposed edge causes cavitation bubbles to form. At a pressure of 2,300 Pascal, a certain mass of water vapor requires over 50,000 times more volume than in its liquid state. The bubbles collapse as soon as they reach a region with a pressure above the vapor pressure. Because water from the vapor bubble occupies 50,000 times less volume after having condensed to its liquid state, the collapse of each bubble is a spectacular event and emits pressure shocks. Pressure shocks from many collapses result in an audible noise very characteristic to cavitation. The sound used now in the video has been recorded in an experimental setup similar to the one in the animation. But how does it look like when cavitation bubbles are formed and collapse in detail? We can see the formation and the collapse of cavitation bubbles with a diameter of approximately 9 millimeters in slow motion. In real time, this process takes about 4 milliseconds, and it is a spectacular physical event. Because liquid water occupies many thousand times less volume than vapor, the bubble implodes. It first assumes a ring shape. Shock waves and a strong microjet are the result of a collapse. Let's go through the whole process again. If the local pressure decreases below the vapor pressure, water evaporates. A cavitation bubble is forming, is growing larger, and is transported with the flow to a region with a higher pressure. The bubble stops growing. If a local pressure exceeds the vapor pressure, vapor condenses, starting from the bubble's wall. Its surface starts to break down at its weakest spot. A microjet forms and pierces into the bubble's opposite surface. The bubble is now collapsing. The bubble becomes a torus and disintegrates further. The microjet continues to flow in the liquid and can hit a wall. Through its concentrated impact, even high-strength material can be damaged. The implosion releases energy in a very short time concentrated in a very small spot. If the microjet hits a surface, it damages the material by a localized short-term overstraining. The material starts to evolve microcracks, and later material can break off. We show a few examples of damage in pump impellers kindly provided by the Swiss pump manufacturer Herney. A brand new impeller to the left, in comparison with an impeller having been continuously exposed to cavitation during 6 months, another impeller with damage from 12 months operation in cavitation, and one from 24 months. The new impeller shows the geometry as it should be under normal operation without cavitation. After 6 months of operation under cavitation, material has been eroded in the center of the wheel. The respective areas are highlighted with grey color. The impeller blades are undamaged. After a year of operation under cavitation, the damaged geometry has a different shape, and therefore the flow has a different pattern. The collapsing cavitation bubbles cause material break-off at the top edge of the blades. After 2 years, the blades have been eroded completely, which makes it impossible for the pump to function. In this video, we have shown the basic mechanism leading to the formation of cavitation bubbles, which reduce the flow of water. We have also seen the spectacular collapse of cavitation bubbles, leading to noise and damage even to high-strength material. Systems have to be designed such that cavitation is avoided.
Okay, so hopefully this is proving to be beneficial to you. There's a lot of stuff covered here, and again, we're without going into great engineering detail, we're kind of covering the highlights of this subjects to give you a little better understanding of what happens inside this pump as it spins. Remember, a pump itself is just a piece of rotating equipment. It doesn't know what you're trying to do, what you want it to do. It only knows what it's designed for, how fast it's spinning, and what you're feeding it. And it's going to try to put out basically as much as it can up to the resistance you create for it. Starting up here, the chart that we're looking at is kind of cool. This is basically atmospheric pressure at sea level right across this line right here to understand this chart. This is about 100 kilopascals. Remember I said the sea level is about 101.3 or something, I think. And at that, we would see that water turns to ice at 0 degrees Celsius, which is 32 degrees Fahrenheit. And it starts to boil at 100 degrees Celsius, which is 212 degrees Fahrenheit. And it follows this line straight across here because the pressure is at that level. However, in a pumping system, if that pressure falls because of turbulence or because of lack of fluid to fill a certain space, if that pressure falls, increased velocity, this line drops. And as this line drops, you can see in certain areas, it will go, water would go direct from ice to vapor, right to steam without even going through a liquid state. If that pressure were low enough. So that's a very violent change. That's not something we would ever expect to happen inside of a pump because we wouldn't ever expect to be able to try to pump ice. But you can see how much a drop in pressure can affect where that water boils at or goes to vapor at. At 50 degrees C, which is off the top of my head, I want to say it's about 120 degrees Fahrenheit. At 50 degrees C, we've already gone to, at about 120 degrees Fahrenheit, to boiling at 10 kilopascals, or about 1/10 of atmospheric pressure. So inside this pump, when we create a lot of turbulence because it's not operating the way we would like it to operate, maybe we've starved it, maybe we've closed off the discharge valve enough that we're causing a lot of recirculation and turbulence inside that pump, we can get to areas where that pressure dropped below that level, even 1/10 of atmospheric pressure. So pump cavitation, as you saw in that video, is very damaging to the pump casing, pump impeller, I've seen areas where you could hardly even tell it was an impeller. The veins are completely gone. It's basically a rotating disc that looks like it had severe erosion or chemical attack, but in fact, it's cavitation oftentimes. And what some of the signs that you're going to see is that flow going through that pump is going to sound like you're pumping gravel. Well, there's no solids going through it, assuming there's no solids in the liquid. It's that formation and collapse of the vapor bubble that's creating that sound. And it sounds like the cavitation sounds like you're pumping gravel. It creates vibration in the pump. Sometimes you can even feel that on the outside of the casing if you put your hand on the outside of the casing as it's running. Please don't put your hand in the area of a rotating shaft. It's not a good thing. I don't speak from experience, but I hope never to make that mistake. It will cause premature seal and bearing failure because of all of that vibration. Again, when we get shaft movement, when we get vibration on a rotating piece of equipment, it causes us to create undue stress on bearings and the seal movement. The seals just do not like an abnormal movement at all. And it certainly would have some effect on power consumption. More noticeably, it's going to have an effect on the amount of flow rate and some pressure decrease because those vapor bubbles are taking up what should be taken up. The volume of it being taken up by water is now being taken up by the vapor bubbles as it goes through this pump. So it affects performance as well, besides damaging the pump and seal. So I said there's several different ways we could form cavitation in a pump. There's two major ways, the first being suction cavitation, and this is caused really by two extreme or low pressure, if you want to call it high vacuum, that's fine, conditions near the suction. We don't have enough pressure of that fluid coming into the suction line to be able to fill all of those veins as this pump rotates. And the pump is being starved. It's not receiving enough flow to fill all those veins. And the vapor bubbles form near the eye of the impeller. They start flowing across the impeller veins and until they reach a point where there's enough pressure that causes that bubble to collapse. If you were to look at an impeller like this impeller is spinning this direction. Remember in that video, we said that this vein tells us that this pump is spinning in a counterclockwise rotation, is spinning this way. So the high pressure side is going to be on the front side of this, on the front side of this impeller vein coming around, because that's what's it's pushing the water with. The low pressure side is going to be on the back side of this vein, on the following side as this thing's spinning. Darn it, I did it again. So what you're going to see is as those bubbles form near the suction eye here, they're going to be filling these voids as this impeller spin in this way. And the low pressure zone is going to be here. Well, as it starts traveling out here, it starts hitting some of this higher pressure area towards the outside of this impeller, and those bubbles start collapsing. And that's why you're seeing this being torn away right here. And I have seen impellers that look much worse than this, much more significant. This actually, because of the amount of corrosion or erosion out here on the side, actually looks like we may at times be having some recirculation cavitation, which is the next type of cavitation. But for the moment, let's look at possible causes of suction side cavitation: clogged filters or strainers on the suction side. Remember I said that a suction strainer can be a good thing for you. It keeps big solids from coming into the pump. But if it gets clogged up and restricts the flow, then all of a sudden we can create cavitation inside that pump. Any kind of blockage in the pipe, we've seen cases where, a towel or a shirt or something along those lines, glove gets down into a pumpage, into a tank, and closes off these pipes or closes off the suction side of the pump. So it's blocking a good steady flow into that pump. Remember, one of the things I talked about in piping design was not having an elbow close to the pump itself. We wanted 5 times the diameter of that suction pipe coming into that pump to get nice, straight, laminar flow. If you had an elbow very close to a pump, it's very possible that you could cause cavitation on some of the veins on the one side of that elbow as that rotates, and then it would disappear as the pump rotates around, and then reappear, all the way around those pump casing or that pump impeller as it's spinning, depending on what side of the intake pipe it's on. So that's why you want have a nice laminar flow coming into this pump. That's why you want 5 times the pump diameter of straight pipe, why you don't want an elbow close to it, because you can cause cavitation just by the disturbance of that flow. Again, it's turbulence. It's an area of low pressure that's causing this to happen. If we operate a pump too far out on the curve, let's say that 435 gallon minute 3x4 curve that we looked at, let's say we don't give it much restriction and it's trying to operate at 650 gallons a minute. Out at 650 gallons a minute, it takes a tremendous amount of inlet pressure to be able to fill all those veins in that same size. And we only have a 4-inch inlet. So our pipe velocity goes up of that flow coming in, the pressure goes down as velocity goes up, and we're less able to fill all those veins. So running out on the curve, not giving enough back pressure, absolutely can cause cavitation on the suction side of this pump. So it gets back to a poor piping design, maybe with that elbow or operating too far on a curve. Like say on that one system that I mentioned that had normal operation would be operating 3 pumps, but at night they thought it would be a good idea to run 1 pump and turn the other 2 off to save energy, which is great. The problem is that it lets that pump run way out off the curve, and all of a sudden they're getting cavitation and seal failure and vibration and cavitation in the system that ends up destroying that pump. What they think is a good idea to save energy is, but they haven't accommodated for the lack of back pressure. The proper thing to do there is, if they wanted to do that, would be to try to spin this thing down in a VFD, run it at a slower RPM, perhaps, depending on the system, where the pump is not trying to put out as much pressure. It changes the pump curve, it drops it down, and therefore our NPSH drops because we're not trying to move as much fluid, and all of a sudden we save energy and help the pump run. So suction side cavitation, those are generally your common causes for it. I mentioned that you could create cavitation on the discharge side as well. If we create too much restriction in this pump discharge so that there's no place for this water to go but back to the low pressure side, what's going to happen is you're going to create little tornadoes of turbulence inside this pump casing as this pump flow tries to relieve itself back to the low pressure side, and it's going to cause these little tornadoes, if you will, and at the center of that tornado is very low pressure. Same thing that happens in atmospheric conditions happens inside this pump. The amount of turbulence that creates this little tornado creates that low pressure zone, and it occurs when discharge pressure is extremely high. It can happen when we're at, say, 20% of best efficiency point. Remember I said we didn't want to operate out too low a flow. Part of it is because of discharge cavitation. The pump is a stupid thing. It's trying to spin at a certain RPM, put out 435 gallons a minute. That's where it's happy. But all of a sudden you've made it try to run at 80 gallons a minute. Well, what happens to that other flow? It gets recirculated across the front of the impeller, across the back of the impeller, across the cut water to try to make it back to a lower pressure area to balance itself out. But in doing so, it creates this amount of turbulence and vibration that causes what we call recirculation cavitation. When you look at an impeller, it's going to have a different appearance because a lot of that turbulence is happening out there by that cutwater and out at the vane tips of that impeller. A lot of that cavitation is going to happen right near the tips of the impeller vanes on the pressure side now, because that's where it's trying to feed back across to go to low pressure side. So this particular impeller that is all pitted, looks like maybe corrosion or something. Most people would look at that and say, well, my chemical must be attacking my impeller. You didn't give me stainless steel, you didn't give me iron or whatever, and it's some inferior material that's causing this corrosion. Well, that's not the case. This is suction side, or excuse me, discharge side cavitation that's trying to relieve itself and go back to the low pressure side. But in doing so, it causes so much turbulence that it causes pockets of very low pressure that then hit a higher pressure zone and collapse. So again, when we look at the curve, if we're way out on the curve to the right, or if we're really far to the left, it's where these bad things happen. Besides having all of that excess shaft movement and vibration and seals failing, we're also tearing up our pump. I've seen within a matter of a couple months, impellers that were destroyed like this. You want a nice smooth impeller to be able to have nice laminar continuous flow through that pump. Something like this is not a good thing, obviously. Okay, so what would cause discharge cavitation? Again, it's somehow or another we've blinded off the discharge of this thing so that we are forcing that recirculation. And possibly a blockage in the pipe, maybe a rag or a towel getting pumped through the pump, but getting caught on a check valve on the discharge side of the pump or a throttle valve and causing that pipe to become even more closed than the throttle valve might be. It may be a clogged filter. A lot of times they'll put bag filters or cartridge filters on the discharge of a pump to catch solids before they go out into a system. And maybe that's a machining operation where they want nice clean coolant that's filtered. The way to do that would be on the discharge side of the pump. And when that filter becomes too clogged, too blinded off, it creates a lot of restriction on the pump, and it causes that pump to run towards the deadhead side of the curve, to the left side of the curve, very low flow, and causes the pump to have to recirculate, because again, that pump's, in the case of that 3x4/8 curve that we looked at, trying to put out 435 gallons a minute. That's where it's happy. If we cause that thing because of too much restriction on the discharge side to run back on the curve and only put out 120 gallons a minute, then that excess flow is going to try to go somewhere, and it's going to be cause turbulence inside the pump. All because somewhere down the line there was a clogged filter. Or maybe we have a system that's pumping through a bunch of nozzles, and 4 of the nozzles out of 5 are excessively worn, and they're too big, and they're not causing enough restriction, and we're running too far out of the curve. Or those nozzles have been blinded off, and we're causing that pump to run way too far to the left on the pump curve. Both of those things can cause cavitation. One's recirculation and one's suction side. So poor piping design is potential. If we had a system or a pump that's capable of, let's say, 40 PSI and at 400 gallons a minute, and we're trying to pump into that 50 PSI header that I said, well, it can't overcome the 50 PSI. It can't open the check valve, for instance, on the discharge side of the pump. So it can't pump any water, but it's still trying to move water. And we're still spinning at 1800 RPM or 3450 RPM. The only thing it can do is recirculate inside that pump, and that's where you would get severe discharge cavitation. It's got nowhere to go. So minimum submergence. What happens in a condition other than, let's say, not enough fluid or turbulence of the fluid causing cavitation, Another phenomenon that can happen in a pump is what's called air entrainment. And when you draw water out of a tank, or you have a vertical pump mounted down into a tank, when the liquid level gets low enough, we can suck air down through that water. A common example of that is in your bathtub. There's a velocity of water going down through a pipe, your drain, that's drawing water out of that bathtub. And when that velocity is at a certain flow rate, or certain velocity flow rate, you can draw air through a vortex of column of water, looks like a tornado, down through the water when the water level gets close enough to that drain. That's what happens. That is a vortex. That is air entrainment. So the drain that's going out of there contains water, but it also contains air. It's easier to suck air into it than it is to suck the water into it when that water level gets low enough. The same thing happens on a pump, whether it's a horizontal pump or a vertical pump. When the liquid level gets low enough in the tank that it's drawing from, and the velocity is high enough of the intake flow, it may be easier to draw air down into it than it is to draw enough water into it. Well, air entrainment in a pump, depending on what type of pump it is not a good thing either. And the percentage of amount of air is determined by the volume of the air, but it is certain types of pump can handle more percentage. When remember that chart that we compared different types of centrifugal pumps, some types of centrifugal pumps, like say a vortex or recessed impeller, can handle up to 30 or 40% air because of their design. Other types of pumps, like say ANSI pumps, can't handle as much air. They may be limited to 3 or 4 or 5% air. Either way, whatever volume of air, it reduces the amount of flow because that air takes up volume, and the pump performance falls different than what the curve says it'll do, because let's say 20% of that volume is air. Well, you're not measuring air in a system, you're measuring water flow or liquid flow. So a system that is 100 gallons a minute with 20% air, you're actually only getting 80 gallons per minute of water flow because 20% of that is air. And your pressure is going to be reduced because, remember, pressure is a factor of the resistance of the system. So if you have less flow, you have less back pressure in a system. There's less friction loss. There's less pressure drop across a filter or across a nozzle, for instance. So you're going to have increase of vibration because that air is partially collapsible. Water is basically incompressible. If you compress water by about 0.5%, 0.5% compression, I believe it goes to about 2,000 PSI. So it's basically incompressible. If you compress air, I think it needs to be compressed about 40 or 50 times to get to about 100 PSI. So it's very spongy, it's very compressible. So what happens is that volume goes up and down as it goes through the pump, and that causes vibration inside that pump, on the shaft, on the impeller, and it causes vibration to the seal, which can cause seal failure. So if you have a fair amount of air coming into the system, because of the vibration increase, you can create seal failures or bearing failures prematurely. You may have, again, a shortened mechanical seal life, premature bearing failure. You're going to have lower flow rates. You're going to have certainly diminished pressures. If you get enough air into a pump, you can create a condition where the pump loses prime. So if we're drawing from a horizontal tank, or a horizontal pump drawing from a tank, if that liquid level gets low enough, it'll get enough air into it to lose prime, even though the liquid level may be above that pump still. Same type of scenario that happens inside your bathtub as the liquid level gets low enough. There are some cheats to be able to try to give yourself the ability to go to lower. It's all about the velocity, the apparent velocity of that flow at the edge that creates that vortex. The higher the velocity of that pipe, of the water going into that pipe, the more liquid covering that pipe, the more height of that liquid needs to be to prevent air entrainment. So that's why we call it minimum submergence. We don't have enough submergence of that pipe or that pump to be able to prevent that vortex of air coming down into the pump. So if you go to a larger pipe on an intake side, even though it's only a 3x4/8 pump, if you put a 10-inch pipe, the velocity goes way down in that 10-inch suction pipe, and therefore you can go down to a lower liquid level in that tank and still not draw air down into that pipe. Hope that makes sense. There are some other cheats that you can work around, but one of the big ones is trying to use a larger pipe. A lot of times when we sell a vertical pump, and they may use what's called a tailpipe that goes down from the pump to near the bottom of the tank, for instance. Most of the time when we do that, we would suggest that they use a larger diameter pipe going down into that tank to reduce that velocity, the apparent velocity, so that we can suck down closer to the bottom of that tank or the end of that pipe. Sometimes we'll angle cut that pipe on the bottom because by angle cutting it on, let's say, a 45-degree angle, we're creating a larger apparent intake of that pipe because of that angle cut, and therefore a lower velocity because the pipe size appears to be bigger to the pump. You'll see a lot of times vertical pumps have a bell intake on them. And again, it's trying to reduce the apparent velocity at the edge of that pipe to be able to draw air down into that pump vortex. Submergence, typically you want to stay at least one diameter off the bottom of the pump, or else you're going to start increasing the velocity if this is a vertical. So the distance of minimum submergence is basically the measurement from the pipe itself to the surface of the liquid, from the inlet suction pipe to the surface of the liquid. And it's very calculable. We have some pumps that were 95,000 gallons a minute, and we made about a 10-foot diameter intake on those pumps. This was at a floodwater project in the Everglades. And we calculated that we actually wanted to go to about a 12-foot intake given the amount of water over the top of these pumps, or submergence, if you will. So it is very calculable, and it can be proven that this is how much distance you need to prevent that vortex or that swirling of water or air going down into the pump. Talking about what the effects are, on say an ANSI pump, 2% air content may reduce the pump flow rate by about 10%. 4% may decrease the flow rate by about 40%. Remember that air is very compressible. So it takes up a larger volume as an air state than it would be under pressure. So ANSI pumps very generally, most close tolerance, if you will, pumps similar to an ANSI generally do not operate well above 4 or 5%. That's pretty much your cutoff. And you can have severe pump failure, like say with one of those type of pumps at 14%. Meanwhile, a vortex pump, a recessed impeller pump as we call it, especially with some special handling, maybe it'll handle up to about 40%. We accommodate in the sizing of those, knowing that we're going to have at times a lot of air. We may accommodate by oversizing that pump to know that we're going to be pumping 30% air. Let's say we want 700 gallons a minute. We're going to have 30% air. We would probably size that pump for something over 1,000 gallons per minute to be able to get there, to get to the 700 gallons a minute. So common misconceptions is that this problem may exist only on vertical pumps. It's not a matter of whether it's a vertical or horizontal. It's all a matter of what that distance is from that pipe to the surface of the liquid. When we do a calculation, that's what it's all about. And it's based upon a large part of that conversation is based on, or calculation is based on the velocity of that flow going through that pipe. Generally, you want to stay one diameter at least off the bottom. The diameter of the intake is important because if you have 500 gallons a minute, for instance, going into a pump, it's all about what that velocity is. Well, the larger this diameter of this pipe is, the lower that velocity is. And there's charts to be able to show that, or calculation on a mathematical calculation to show what that velocity is. And the other important things when you have pumps like this, let's say you have even a horizontal where you may have two intakes coming off the bottom of a tank, is you want separation between those pumps, between the verticals or between those intakes, so that you're not creating a lot of swirling disturbance of water trying to come into that pipe. Oops, I'm sorry. Trying to come into this pipe, being affected by a pipe that's too close to it, by the turbulence that's around that. Again, you want smooth laminar flow coming into a pump, whether it's a vertical or horizontal. So in this case, they're recommending that you have at least 3 diameters of this pump intake between centers of these pumps, which are verticals, or between centers of suction pipes if they're horizontals. Again, we're trying to get clean flow, nice, smooth, clean, consistent flow into that pump. Pump's going to be happiest when we have that. We want happy pumps. Okay, so I said that this is all a calculation, and it's in the Cameron Hydraulic Data book. If you have that, or Crane technical paper about flow of liquids, you can calculate the velocity pretty easily. Velocity is a matter of this formula right here, where you have velocity in feet per second, and it's the diameter is the suction pipe diameter here. Whatever the gallons per minute is here. You can create what that velocity is going into a pipe. And then there's charts that show you how much minimum submergence you need. Rather than having to do the full calculation of minimum submergence, you do the velocity calculation, look at a chart, and then be able to tell how much minimum submergence you need of that intake, whether it's a vertical or horizontal pump, to the liquid level that's above it. Hopefully I've said that right. You can also do the calculation, which is what this is, and I don't think you need to memorize this. This is HI standards. This came out in 2016, Hydraulic Institute standards. And this is the calculation that's most commonly accepted. However, on this next page, I'm doing a calculation. I have a spreadsheet that each one of these is a different formation of a calculation by different people. These are engineering firms that had these out. Some of these may be based on a particular pump manufacturer, for instance, Prosser, that all had a formula to be able to create what the minimum submergence was required at 150 gallons a minute through a 2-inch pipe, which is 15.32 feet per second, is what the velocity rate of that flow is coming into it. The HI standard 2016 says 10.8. You'll see some of these agree with that. Some of them don't. This is a fairly evolved calculation because there's an abbreviation for a calculation here that is fairly evolved. But the important thing is here, if we show 150 gallons a minute through a 2-inch pipe, it's 15.32 feet per second. We need 10.8 inches of submergence, right? If we look at the next page, I've done the same thing now, but I've done a 3-inch inlet. The velocity drops to 6.81 feet per second of that flow because of the larger pipe size. And the minimum submergence now is only 7.8 inches as opposed to 10.8 inches. So we've reduced the minimum submergence by 3 inches, which would mean that we could be, the water liquid level could be 3 inches lower and still not create that vortex of air coming down into a pump. If we went to a 4-inch, it would be even lower. There is some diminishing returns where you can't get much lower. Some of the cheats that I mentioned before, if I go back to this particular drawing here, remember it's about velocity here. So we could create a larger opening, larger pipe size, or one of the cheats may be is we put a flat sheet across here, maybe steel sheet that is, let's say, half a circle of, I don't know, 18-inch round half circle. So a 9-inch radius or a 12-inch radius, whatever. And it's a half circle that's welded to this tank above this line. And what happens is the apparent velocity at the edge of that plate is much lower, and therefore it doesn't create that vortex that comes down into the pump or into the intake, because we've created a shelf above it that the apparent velocity at the edge of that plate is low enough. The same thing could happen in a situation like this by putting a flat plate over the top of this and forcing the air or the water around that plate. The apparent velocity at the edge of that plate is low enough that we could draw this liquid level down to a lower level before we draw air into that pump. That's what we're doing in a sense with these bell intakes. If we made this a larger bell, we could draw the liquid level down closer before we start drawing air into that pump. And again, air is a bad thing. It's going to cause vibration in the pump. It's going to cause seal failures. Any question on minimum submergence? I said that before that I have a technical data sheet in an Excel format. It's a worksheet. One of the pages on it is this calculation. So you could plug in 150 gallons a minute through a 3-inch pipe. It tells you what the velocity is. It tells you what your minimum submergence needs to be at that velocity rate for you to prevent a vortex of air. Again, the whole point of all this conversation is how do we make a pump run the smoothest with the least amount of problems over a long period of time. One of the things that we're going to be promoting heavily this year, and this whole conversation I hope is not come across as a sales pitch, because it's really not, but this is a cool device that we're going to sell. We're going to focus on marketing this year, focus concentration on. What this is a vertical sealless pump. And remember I said that seals are one of the first things that fails in a rotating piece of equipment, the sealing method, because of shaft vibration and stuff like that. Well, this is a sealless pump. So the cool thing about this is this can replace an ANSI pump, for instance, outside of a tank. You would plumb in from the tank like you would an ANSI pump, the suction line coming into the bottom of this. The discharge would come off of the side of this like an ANSI pump, and this can be an ANSI wet end, or this could be a vortex wet end, or whatever it is. This thing is mounted outside the tank. The tank would be over here. Liquid level would be somewhere up in this area, for instance. And whatever makes it, this pump is allowed to leak internally inside this column, as we call this an enclosed column. And whatever leaks past the bushing that's in there, which is normal operation, would build up in this column, and then we would take a pipe or a hose from this port right here, either back to the suction side, so it could be brought back into the suction, or from this pipe or from this port, it would be pumped back over the tank so it can drain back to the tank. But this becomes a sealless pump mounted outside of a tank. You eliminate all the seal failure problems, and pump people tell you that 85% of the time that a pump is pulled for repair, it's pulled because of a leaking mechanical seal. 85% of the time a pump is pulled for repair, it's pulled because of a leaking mechanical seal. It's the first thing that fails. Generally, when they replace a mechanical seal, they'll replace bearings and stuff like that as well, but those generally are not worn out as soon as the mechanical seal fails. By going to this type of system, you can allow a customer that has a lot of seal failure problems to be able to install a pump that can handle more air, it can handle more bad things going on in the curve because it's sealless. It doesn't have that weakness in that chain, and this is going to be something we're going to promote heavily this year. And it's really nice something to have. Now, one of the minimum constraints here is that this cover plate, this area right here, there's bearings in this bearing housing. This cover plate that's at the top of this stand has to be above the highest liquid level that that tank would ever have. So that liquid level, maximum level, has to be below this plate. We can mount this up in the air 30 feet, that's no problem. We can make this pump longer to get that suction down lower. The other constraint is that when this pump starts up, the liquid level has to be at least above this casing. So you've got an operating range, and we can make this pump longer between here and here, but your operating range and the tank level is somewhere in this range. Now, when the pump is running and it's primed and running good, the liquid level could drop down below this casing and it would still draw liquid up into this pump until such time that liquid got so low that we drew air into it and it would lose prime then. So, and we can make this pump actually be able to run dry, meaning that if we suck so much air into it that it lost prime, it would continue to run without being shut off, without damage, until that liquid cable came up to another level where it would be able to prime again and be able to get into the pump and prime it up again and take off and pump fluid. So any questions on that? That's a pretty cool device. It's something that we have quite unique to us, and it's going to be I think a very big seller for us going forward because it can eliminate a lot of problems in the system. Any question on that? And if you do have questions, we can address those further before or going forward. Okay, so I turned my video back on because I'm going to show you a couple things as we go forward. We're actually going to get into some troubleshooting of these pumps and systems. And in performance tests, as tools to you, what do you have? You have pressure reading off a pressure gauge. That's the most common thing that you're going to be able to look at to be able to determine where a pump's running at, what condition it's running at. Most systems, you're going to have a very difficult time knowing what flow rate you're at. That's why I said at shutoff or at zero flow is about the only time that you know exactly how much flow that pump is producing. Most systems don't have a very reliable way of telling you how much flow you're getting. So if you had a pressure reading and then you went back to the curve, you could guess about how much flow it is based upon how much pressure you're getting out of that pump. The other thing that you can measure pretty easily is how much amperage that pump is drawing on the motor. So by knowing those three pieces of information or two of them, you can go back and look at a curve and say, hey, that looks like we're running about 300 gallons a minute. And the amperage draw matches what I'm guessing the horsepower is at that point. That's probably we're running about 300 gallons a minute. You can know that we're doing pretty good. You can also look at various flow points and try to get some kind of a reading. For instance, you may take a pressure reading at deadhead. You may take a pressure reading at 30 PSI out on the curve and do those same type of things as far as gauging where a pump is operating at to see if it makes sense to the curve. And then, of course, deadhead pressure. Do not operate a pump at deadhead very long, but it's okay to operate it for a very short period of time to be able to get a pressure reading. Again, at the very far left of that curve, a pump curve isn't always 100% accurate. It may have some variation because of all that turbulence that's going on inside that pump at deadhead. You're trying to force all of that flow back to the low pressure side. So yeah, it's not 100% consistent, but you should get at least relatively close. The other troubleshooting senses that you have, I mean, to be able to judge flow rate, about the only way is ultrasonic meter or some kind of flow meter in a system, or maybe a bucket test if it's a flow enough rate, where you actually measure how much flow is coming out of a system in a bucket and time it. But the other things that you have are sensory tests. What does it sound like? Does it sound like you've got cavitation going on? Does it sound like it's running nice and smooth? Is there some kind of a squealing noise? Is there some kind of a grinding noise? Whatever it might be, does it sound like there's gravel going through the pump, which would either be gravel or it would be cavitation? What temperature are things running at? And one of the things that I wanted to show you is this is a FLIR thermal thermometer, yeah, I guess it would be a thermometer that you can use, and hopefully it's going to start up here. It's a little device, looks like a cell phone actually. And this is a camera that senses temperature points on a given system or bearings or an electrical box. It's pretty useful. If you look at it here, looking at me, you'll see a temperature variance, and these things are about $600 or so. It's really nice for a service department to have. And you'll see where the hot spots are, and you'll be able to tell here, if I'm looking at this right, you'll be able to tell actually what temperature something is at. We've had cases before where we had bearings running very high temperature or an intermediate bearing on a long pump. And something like this is made by FLIR, F-L-I-R. It's available on Amazon. It's really a cool thing. It's rechargeable. You can take pictures, and when it takes a picture, it actually takes a physical picture like your camera phone does, but also takes a thermal picture so that you can include it in a report to be able to give to somebody of a failure type thing. This is really a nice device to have. About $700, I think, when I bought it. I don't know what they are today. The other thing that's really cool to have as far as a device is an infrared thermometer. And this you would just point at a surface and it would then tell you what the temperature is. And if you moved it around on a surface, it would tell you what the lowest temperature and what the maximum temperature of something that it picked up at. Right there, it picked up a maximum temperature of 91.7 of all those things that I just pointed it at. This also has a laser pointer on it to tell you where you're pointing at, a little red laser beam. If I can turn that on. Okay, so you can tell right where it's pointing at and what temperature that is running at. Now, don't get me wrong, temperature on your face is never going to be as hot as what your internal body temperature is at, but it's a pretty cool device. And they're actually using these things now for taking temperatures for people that may have the COVID-19 virus, so they don't have to touch them. They use a thermal thermometer like this, infrared thermometer. And they have one that can go inside your ear and take your temperature there. These are inexpensive and they're really nice to have. You can point it down at liquid to see what temperature the liquid's at. You can point it at the circuit panel to see if sometimes if you're having a high amperage draw, it may be because you have a bad electrical connection. And sometimes you can pick it up with one of these or one of these to be able to tell where, if it's got a bad electrical connection, there's going to be more resistance there, there's going to be more heat there. You'll be able to tell with one of these things if maybe you got a bad electrical connection. There may not be anything wrong with the pump. It may just be a bad connection, wire connection inside the circuit box. So all of these things working together, vibration, you put your hand on the pump. Is it running smooth? Is it, does it feel like it's healthy and happy, or does it feel like it's angry and upset? There's probably a reason for it. It may be an alignment issue. It might be cavitation. It might be air entrainment. There's a lot of things that can cause vibration as this thing runs. But between the combination of the sound, the temperature, the vibration, pressure reading, conversion back to a curve, you can oftentimes tell if a pump is running where you want it to run, if it's running out off the curve. It really helps you define why a pump failure is happening. Why does a pump vibrate? Bad operating conditions. We've talked about both sides of the curve, left and right. Are we too far towards deadhead? Are we too far out on the curve? I guess if I'm looking at it from your perspective, it would be the other way around, too far left or right. I'm hopelessly right-handed, by the way. Coupling alignment, if the shafts aren't in line to each other, both vertically, horizontally, and angular, you're going to get vibration of that thing running. And especially if those things are moving, you're going to get a lot of vibration. Like I said, the pump on the mezzanine where the whole bed plate and the whole mezzanine was moving as you walked around this thing, boy, you're going to get vibration from that alone. And it's going to cause bearing failures. It's going to cause seal failures if it's a sealed pump. One of the cool things about that pump that I said that was sealless, that vertical that replaces the ANSI, is that all of those fits together all the way up and down that pump are all C-face rabbited indexed fits. So there is no coupling alignment and there is no motor to shaft alignment. All of that's done for you. It's all fixed and mounted. What other things can cause vibration? Cavitation, air entrainment. We talked about that. Improper mounting of the bed plate. Solids going through the pump. I mean, we have pumps in the Nagel pump line, for instance, and the Gusher pump line that are meant to be able to handle solids. We had a pump at Honda Anna, an engine plant in Ohio for Honda Motors. And as the system was built, somewhere along the line in construction, a piece of 2-inch by 18-inch long angle iron, 2-inch angle iron, 18 inches long, got into this tank. And we had a 6x8 15, two of them actually in a pump back tank that were drawing liquid out of the bottom of this tank. And we got a call one day that our pump was vibrating and rattling and all kinds of bad stuff. And we go and look at it, and sure enough, it's rattling and vibrating and all kinds of bad stuff. And we shut the pump off, and the rattling goes away when we turn it back on. And geez, I don't know what's going on with it. Pull the pump out and inspect it. Nothing wrong with the pump. Put it back in the hole, and it's running nice and clean and no problem. And then we get a call a week later or 2 weeks later, and the pump's rattling again. We go back and try to figure this out. Well, it was pumping water-soluble coolant, which is oil mixture and water, and it's meant for machining operations to be able to cool the machining tips, the drill, or the whatever it might be, a machining operation of metal. And it's milky in appearance, so you couldn't see down into the tank to be able to see there was a 18-inch long by 2-inch angle iron. Well, several times we pulled this pump out, and this pump is like 9 feet long and weighs, I don't know, 4,000 pounds or something. So we pulled this pump out finally one time, and there it is sitting in the pump casing. And this was a recessed impeller vortex pump. Well, this pump had pumped this 2-inch by 18-inch long angle iron several times through the pump, and it got caught going to the discharge valve, the check valve and the throttle valve and the discharge side of the pump, and couldn't make it past there. Well, it would sit there and rattle, and that's what was rattling and causing all this vibration and stuff. When you shut off the pump, the thing would drop back down into the tank generally and drop, and we wouldn't be able to see it. Well, this one time when we pulled it out, there it was inside the casing of the pump sitting there, and all of a sudden we knew what it was. To testament of our pump, it didn't damage the impeller blades at all, because a recessed impeller, generally most of the fluid going through that pump, the way it's designed, most of the fluid going through that pump never touches the impeller. It's all done by induction. But things like solids can certainly cause you a lot of vibration. If you if you have a solid come through a pump, and let's say it bends one of the 6 vanes on that impeller as it's going around, well, if that one vane is bent, it could be bent outwards or bent inwards, it's going to do either more or less work as it's spinning at 1800 RPM in rotation. So all of a sudden we've thrown that pump out of balance because that one side of the impeller, as it's rotating, is trying to do more work. It's moving more fluid or less fluid, depending on which way it's bent. And it's going to throw the thing out of mechanical balance. Well, okay, so you're going to get a lot of vibration from that. You could get, maybe somebody has a glove or something that gets thrown into the tank and you get a glove stuck in part of the impeller vane, in one of the vanes, and the rest of the vanes are nice and open and it's still moving fluid. Well, you throw it out of mechanical balance too, because there's no work going on in that one vane or 2 vanes that's clogged, and all the rest of them are open, so they're doing work. So all of a sudden this thing is way out of balance going around. Maybe you've got a solid that came through that broke off part of a vane. That vane's doing less work, it's going to throw it out of balance. A lot of things that can happen inside this pump will cause that vibration, and vibration is going to cause mechanical seal failures, and it's going to cause bearing failures. It's going to cause those relatively quick. When I said that you could take amperage reading and go back and look at the curve to try to determine where on the curve you're running based on horsepower load, this is a general formula to be able to go back and determine how much brake horsepower there is, to be able to cross-reference back to the pump performance curve. So if you took an amperage reading, let's say it was 7 amps, okay? And if you knew that you, or thought that you were running 400 gallons a minute at 100 foot ahead, and your specific gravity, let's just for simplicity say it's water, so that's 1. So we basically wipe that off the top. It's gallons per minute times foot ahead. 400 times 100 is 40,000, right? I think so. Divided by 3960, which is a constant conversion number, times the pump efficiency. If the pump efficiency at that point on the curve where you think you're operating at is 60%, that would be 0.6 here in this formula. And that would give you what brake horsepower you should be really operating at. And you can convert that over the curve. It should be the horsepower line on that curve. This is just a little more accurate way to measure it. And then if you knew that you were supposed to be running at, let's say 10 brake horsepower, I can tell you that at 460 volts, there's going to be about, and I think that's on the next slide here, there's going to be about 1.15 amps per brake horsepower at 460 volts, give or take. It a little bit depends on the efficiency of the motor and how much more losses you have, but that's a pretty good approximation. So if you know that you've got 10 horsepower, or say 7 amp reading divided by 1.15, you're actually running somewhere around, I don't know, what would that be, 8 brake horsepower or so. And if that matches where you think you're at on the curve, based on the curve and the other calculation that we just did, then it's a cross-reference to be able to determine if you're operating where you think you should be. So it's another cross-reference back to the curve. And a lot of these things, when you go back to the curve, it can tell you how healthy that pump is. If you've got a lot of slippage, a lot of wear inside that pump, it's going to become less efficient. So your efficiency number changes, and therefore your amperage is going to go up for a given amount of work because your efficiency drops. So if we're at 230 volts down at the bottom here, it's about 2.3 amps per brake horsepower. So hopefully this will help you kind of cross-reference back to a curve when you do some testing or failure analysis or whatever it may be. customer may ask you why my pump's not performing, and you're going to go out there and look at a system and try to determine why this pump isn't meeting what their expectations are. It may be a lack of back pressure. It may be starved intake, clogged suction, whatever it is, but you're going to be able to go back and try to determine where the pump's operating on the curve. If it's operating what you think it should be on the curve, then you can kind of rule out a pump problem and more focus on the system problem. One of the things I said was a pretty accurate test was within reason is deadhead test. Again, the curve is unreliable at that point, but it's going to give you an approximation. If you do a deadhead test, which is about the only place on a curve that you know what you're operating at is at zero flow. If you do a deadhead test and a pressure test there, if those two things are in alignment, then you know that that pump's fairly healthy itself. It may have some blockage somewhere, but at zero flow, blockage and friction loss is basically thrown out the window because it doesn't exist. Friction loss doesn't exist at zero flow. So a deadhead test can be really helpful for you. Again, you don't want to operate there very long. You want to take a quick run to deadhead by closing a discharge valve. Never close a suction valve, ever close a suction valve. Close a discharge valve to cause a deadhead, and take a quick pressure reading and maybe a quick amperage reading. So hopefully that will help you time to diagnose a pump too. This again speaks to that deadheading for any long period of time, but it's okay to take it to a short-term deadhead. And by short-term, I mean as quick as you can make it, 5 seconds, 10 seconds, and then hopefully gradually open the thing back up and get flow going back through it again. I did want to talk a little bit about lubrication of bearings. I think that's something to, in terms of life of a pump, to talk about as well. There are really 4 ways to lubricate a bearing. You have, first of all, of course, grease lubrication. Then you have oil bath. You may have an oil spray where they're actually spraying oil onto a bearing, or an oil drip. The best type of lubrication of any kind of bearing is actually an oil spray, where that spray is coming onto that bearing on a consistent basis. It's getting a nice lubrication as it's running, and that's the most reliable. However, that's the most expensive and most difficult way to lubricate a bearing. You will find that sometimes on big turbines, like say at a power generation plant or something on those lines, they may use a spray bearing lubrication, but normally it's an oil bath, where as the bearings are going around, the balls are going around on a bearing, towards the bottom of that, they splash into a bath of oil. You never want the oil level too high on that bearing surface. You just want it at the bottom, so it's splashing in and carrying that oil up around the race of the bearings as they're rolling around in there. An oil mist is really nice. Oil bath is pretty good as well. However, any kind of oil lubrication really depends on that oil to be there. And in plants, oftentimes today, they don't have a lot of preventive maintenance there that goes out and checks oil levels on a very consistent basis. They're shorthanded, everybody's leaned out. So running a bearing without oil, if it's an oil bath bearing, is really a bad thing. And again, on that bearing rotation, you only want it to splash in the bottom. So there's only a little bit of oil level changed where it goes to completely dry to having the right amount of oil. And so if it loses some oil somewhere or another and it gets down below that, you're running that bearing dry, it's going to fail quick. The other type of lubrication is grease lubrication, and that may be a grease lubrication that you manually go out and pump grease into that bearing. You should pump grease into a bearing when it's shut off, not when it's running. Pump grease into that bearing, and don't over grease, because if you over grease, the bearings won't roll when it starts back up. It'll try to push the grease out of the way, and the ball bearings will slide and scratch the race rather than roll on the race. And you don't want that, because if you scratch it, you're going to create scratches in that bearing, its ball bearing itself, and also in the race. So you want to be careful about over lubrication of grease. And you don't want to grease too often, and you want to grease when that bearing is off. If you have the opportunity, it's really nice to be able to grease the bearing and then rotate it by hand a little bit before it's turned back on, if you have that ability to do that. Make sure you lock out a motor before you go greasing bearings and turning the shafts. You should not mix grease types if you're going to do grease lubrication. Grease types, some types of grease will interact with other types of grease, and they'll break down, and it may leave that grease basically unusable. What's left, it may gel, or it may drop the oils out of suspension and turn to liquid, and cause that bearing to run dry. So you should check and recommend what type of grease the plant uses, and match that. If you tell us what type of grease a company uses, we will do an initial charge of grease on those bearings to match that plant as well, the best we can. So don't mix grease types. The other type of grease lubrication is greased for life. And those bearings basically have shields on both sides of the bearing race. And there's grease that's pumped in at the bearing manufacturer, and from then on, grease is never added to that bearing. And this would be really useful in an area where there is virtually no maintenance on these pumps at all. So depending on what plant you're talking about, if they have virtually no maintenance, you'd be better off with a grease for life bearing. It's going to be the shortest life bearing, but it's going to be the longest life if you have really bad maintenance. The next option up from that would be a re-greasable bearing. That's going to be the next longer life to a grease for life bearing under normal circumstances. But again, it's dependent upon somebody going out there and greasing those bearings every so often. Motors have to be greased. Vertical pumps have to be greased. There's no choice. Horizontal pumps, you could do a oil bath, you could do an oil mist, or you could do a grease or grease for life. We have all four choices available for horizontal pumps. Okay, we're just about finished at this point. One thing I wanted to talk to you a little bit about is if you have a customer that has pump problems, I would strongly suggest that they get into a routine of documenting the repairs. Seeing broken pieces and parts and seals that have failed are really help you diagnose what's going on in the system. Pump problems that are recurring for a reason. This pump is designed to run for many, many years. If you abuse it, you can cause the thing to fail in a couple of days, like I said before. If you give it the right conditions, that pump is going to live for a very long period of time. So I would really encourage you to have your customer document repairs, when they happened, any things that happened around there. Was there a long period of shut off in the plant? For instance, was there Christmas vacation or spring break, or midsummer shutdown or something like that? And they came back in operation and started this pump up, and a week later, or a couple days later, or even that day, the pump failed. Okay, that's nice to be able to note in that document that when that occurred. It's good to be able to see broken pieces and parts. And part of that documentation is, why was the pump pulled out? Was it pump pulled out? It's hard to talk. A pump pulled out because the leakage of a seal? Was a pump pulled out because it was making too much noise? Was it tripping the breakers and creating too much amperage? Any details. We get pumps sent back to us all the time, whether they want a pump fixed. Yeah, we can tell sometimes from pieces and parts what happened, but sometimes it's chicken or the egg. which came first? Did cavitation cause the seal leakage? Did the seal leakage or seal failure cause air to come into the pump and cause what looked like cavitation from air entrainment? I mean, there's a whole bunch of things that could happen here that we don't know just by looking at the pieces and parts. So any kind of information that can help you in your repair process or help your customer understand what's going on, especially with a pump that fails on a semi-regular basis, helps diagnose what's going on. And if you've got a customer that's got a problem pump, it's not the pump. It's something in that system or something in their operation, like that installation that I told you that was meant to operate with 3 pumps, and they'd shut 2 off to try to save energy at night and just use 1 for circulation. Running that pump off the curve at night caused that pump to be a problem pump. It wasn't the pump. It wasn't the seal. It wasn't the motor. It wasn't anything. It wasn't even the system. It was how they operated the system. So trying to get back to a root cause, any piece of information you can piece together from your customers, and sometimes there's not a lot of information, can really help you determine why a pump failed. And that really brings me to the end of today's presentation. And I'd like to open it up to any questions. And I want to thank you again for your time. I know I get a little long-winded here and talk about some stuff that is kind of difficult to follow on first pass. But if you have some questions, it would be a great time to talk about them now.
Hey, Dan, can you explain, you had a slide that was talking about diagnosing issues within the pump, and it said something about the uses of amps.
Sure. All right. So basically, when we look at, say we take an amperage reading, we can then convert that amperage reading to brake horsepower. And if we go back to the performance curve itself, let me try to get back there. It was a long way back in this presentation. If we get back to the curve itself, and we let's say we're running 7 amps, which is roughly about 8 horsepower, okay? So 8 horsepower, we know should be somewhere right in this range right here, unless there's something strange going on. Okay, so if we know that we're running about 8 horsepower, but we're not matching with this impeller, we're not matching this pressure, and if we have some kind of a flow meter on this thing, if it's not matching that general area, give or take a few percent, 5–10%, then something else is going on. Maybe it's worn bearings causing too much friction. Maybe there's something interfering with that rotation of that impeller. Maybe there's something blinding off the impeller, partially causing a difference of performance. But all of these things should correlate to each other: the horsepower, the flow rate, the pressure rate, and they all should pretty much match what this curve says. Again, if you knew that you're reading amperage at about 7 horsepower or 7 amps at 460 volts, that's roughly about 8 horsepower, right? So you should be running somewhere in this ballpark. If I did the math right there, I may have gone the other way, maybe 6 horsepower, but whatever that number ends up being, you would come back to the curve and say, okay, based on horsepower, I should be somewhere here. If you have any way of approximating or measuring flow rate, which is often difficult, you probably can't. Most systems you can't, but you generally have a pressure gauge. If you read that pressure gauge and you come up with where you know, for instance, 70 foot of water would be 30 psi, or maybe 30.5 psi or something here, and that approximates what your amperage rate at, that's pretty much where you're operating at on this curve. You know you're pretty close to that. So diagnosing pump performance problems, if you have an amperage reading and you know what voltage you're running at, then you can come back to the curve and you should be able to tell where you're at operating on this curve. If you're not there, it may be a really worn impeller or impeller casing. It may be something interfering with that rotation. You know, a lot of things could go on. If you're underperforming, it may be air entrainment or cavitation or something too. All of this stuff kind of correlates to each other to be able to tell you kind of information, at least give you a very educated guess, if that makes sense. The curve on a pump is your Bible. It is what you go by and what you live by in being able to diagnose this thing. So again, you're picking a pump, you want to be somewhere here. And we're going to have a session that really talks about how do you calculate feet of head in a system. It got pretty lengthy trying to do it today, but basically it's friction loss and the amount of lift that you do in a system is how much resistance there is there. But we're going to have a session on a little bit more advanced course than this on being able to try to predetermine how much resistance you're going to have in a system and determine head. Normally a customer is going to tell you, I want so many PSI or so many gallons a minute at so much feet of head. They're going to tell you gallons per minute at PSI. Most people speak in PSI, or so many gallons a minute in feet of head. Remember that if they tell you in PSI, you got to confirm that it's water, and you should really confirm what temperature approximately that water is at, because that's going to tell you certain things like NPSH concerns, and it's going to tell you the specific gravity of that water, because it varies a little bit, not a lot, but you know, at 180 degrees, water is lighter. It's getting closer to boiling. It's lighter per volume per gallon than it is at 60 degrees or 40 degrees. It's interesting, as water goes to ice, it reaches its maximum volume at about 4 degrees Fahrenheit. So it actually gets larger as it freezes. That's why pipes break. Once it freezes, it may not break if it's at 28 degrees Fahrenheit, but as it gets colder, it expands even further once it's in solid form, and reaches maximum expansion about 4 degrees Fahrenheit. So water changes as temperature changes, and even with water, it's good to know approximately. Now, don't get me wrong, 1.01 specific gravity in the grand scope of things doesn't matter. It's all, it's within the tolerance of how accurate these curves are. Generally, curves are accepted to be +0 and -0.5% in terms of curve accuracy is generally an accepted ratio. Meaning that every single pump that's built is not built exactly with the same tolerances from the front of the vane to the front of the casing, or from the back side of the impeller to the back side of the casing. There is some variance in manufacturing there that happens. It's going to cause some fluctuation of this curve, but it's very minor. All right, I'm going to conclude the session at this point. I am going to leave it open at Lisa's request for a couple minutes, but I'm going to turn my mic off. If you come up with something, let me know, and my video off, and Lisa can copy the email addresses and go from there. But I do thank you for your attendance, and hopefully it's been helpful to you. And if there's anything else that we can do, we're going to have other courses. As I mentioned earlier in the presentation, we're going to have other courses available over the next few weeks. You know, we're all in that situation. Most of us are pretty locked down. Customers probably wouldn't want to see us if we wanted to go see them. But these are some of the other courses that we'll probably, in very short period, have available as well. We're going to make this webinar today available to you for download, as well as the videos that we showed and the presentation that I used. And please, ask questions, gain knowledge, and you will gain knowledge through experience. But there's all kinds of things that happen in pumps, and we certainly, for the new people here in pumps, we certainly welcome you into this industry, and we want to help you succeed going forward. So thank you.